Voyager 2 is 21.4 billion kilometers from home, and it just proved that everything scientists believed about one of the planets it visited was wrong for nearly 40 years. Not because of a mistake, not because of bad data, but because the truth was sitting inside its instruments the entire time, waiting for someone on Earth to finally understand what they were looking at. And the strange part is this. The spacecraft that made this discovery isn't fully working anymore. It is dying slowly, deliberately, instrument by instrument, and yet it just rewrote a chapter of planetary science from a flyby that happened 4 decades ago. Read that again. A discovery from 1986 is only being understood now, in 2026, and what it reveals changes the way we think about an entire planet. To understand why this matters, you have to understand what Voyager 2 actually is and what it has already survived. Because this is not a story about a machine. This is a story about the outer edge of human reach, and about a 49-year-old signal traveling across the dark, still refusing to stop talking to us. Voyager 2 launched from Earth on August 20th, 1977, 16 days before its twin, Voyager 1, even though it was designed to arrive at its destinations later. It was never supposed to be the quiet one. It was built for a mission so ambitious that NASA had originally planned to send 4 separate spacecraft to accomplish it, a grand tour of the outer planets that would have cost over $1 billion and required a level of engineering complexity nobody could guarantee. That plan was canceled in January 1972, largely because of anticipated costs, and NASA proposed instead to launch just 2 spacecraft toward Jupiter and Saturn. But here's where it gets interesting. Voyager 2 didn't just complete that scaled-down mission, it exceeded it. It became something no other spacecraft in human history has ever been. Voyager 2 fulfilled its primary mission by visiting the Jovian system in 1979, the Saturnian system in 1981, the Uranian system in 1986, and the Neptunian system in 1989. Think about what that actually means. One machine launched with 1970s technology, computers with less processing power than a modern calculator, successfully navigated a chain of gravitational slingshots across billions of miles of empty space, threading itself past 4 planets in a sequence so precise that a single miscalculation at any stage would have doomed everything that came after. And it did this while carrying instruments sensitive enough to detect magnetic fields, radiation belts, and atmospheric chemistry from millions of kilometers away. This wasn't luck. This was one of the most quietly audacious engineering achievements of the 20th century, and most people alive today have no real sense of how close it came to being impossible. At Jupiter, Voyager 2 didn't just take pretty pictures. It transmitted new data on the planet's clouds, its newly discovered moons, and its ring system, along with 17,000 new images. But the deeper story is in what it found that nobody expected. Where the earlier Pioneer spacecraft had detected almost no atmospheric change between their 2 flybys, a Voyager 2 detected significant changes in Jupiter, including a drift in the Great Red Spot itself, along with shifts in its shape and color. A storm larger than Earth, one that had raged for centuries, was caught in the act of changing. That should have been the headline of the decade. Instead, it became a footnote, because Voyager 2 was already moving on to something even stranger. At Saturn, the spacecraft photographed moons that would later become central to the search for life beyond Earth, worlds like Enceladus, whose icy surface would only decades later be understood to hide a liquid ocean. But this is where the mission's story begins to escalate beyond planetary photography and into something closer to a mystery investigation. Because Voyager 2 wasn't finished. It had one more decision to make, and mission planners made a call that would define the next 4.5 years of its existence, and arguably the next 4 decades of planetary science. They pointed it at Uranus. Although Voyager 2 had already fulfilled its primary mission goals with the Jupiter and Saturn encounters, mission planners sent the veteran spacecraft toward Uranus, a journey that would take about 4.5 years. Nobody had ever been there. Nobody knew what they would find. And what most people are not seeing, even now, is just how narrow that window of opportunity actually was. Because of the geometry required to set up a future encounter with Neptune, Voyager 2 had only 5.5 hours of close study during its entire Uranus flyby. 5.5 hours. That is the entire window humanity has ever had, in the whole of recorded history, to closely examine an ice giant 7 times more massive than Earth. Everything we thought we knew about Uranus for the next 40 years would be built on data collected in less time than it takes to watch 2 feature films back to back. On January 24th, 1996, Voyager 2 made its closest approach, coming within roughly 81,500 kilometers of the planet's cloud tops. What it found didn't just add to our knowledge, it broke the assumptions scientists had walked in with. The spacecraft discovered 10 previously unknown moons, 2 new rings in addition to the 9 already known, and a magnetic field tilted 55 degrees off the planet's rotational axis, an offset from its center. No other planet visited up to that point had shown anything like it. Every other magnetic field in the solar system roughly lined up with the planet's spin. Uranus didn't play by the rules. Its magnetic field even produced a helix-shaped magnetic tail stretching 10 million kilometers away from the sun. And this is where everything changes, because buried inside the data from those 5.5 hours was something that wouldn't make sense to anyone for another 39 years. When Voyager 2 flew past Uranus in 1986, it recorded radiation levels so extreme that they baffled scientists for nearly 40 years. Not slightly higher than expected. Extreme. The kind of reading that makes a research team wonder if their own instruments malfunctioned. For decades, this anomaly sat in mission archives, an unsolved footnote attached to an otherwise triumphant flyby, filed away as one of those cosmic mysteries that might never get answered because humanity had no plan, and still has no plan, to send another spacecraft back. Uranus is not a priority destination. It is not getting a follow-up mission next year, or even next decade. Whatever secrets it holds, we were going to have to extract them from 39-year-old data. Or not at all. And then, this year, the team did exactly that. Researchers at the Southwest Research Institute announced that they may have finally solved the puzzle behind the unusually intense radiation belts Voyager 2 detected around Uranus. But here's where it gets worse, in the best possible way, for anyone who loves a story about hidden truths. The new research suggests that Voyager 2 didn't just capture an ordinary flyby of Uranus in 1986. It caught the planet in the middle of a rare solar wind event, one that flooded its radiation belts with extra energy, essentially recording the ice giant during a freak cosmic storm rather than during normal conditions. Which means the data that shaped 4 decades of Uranian science may have been describing an exception, not a rule. What most people are not seeing is how enormous that implication is. Every textbook diagram, every simplified model of Uranus's magnetosphere that scientists have taught to students since the late 1980s may have been built on a snapshot of the planet at its most extreme, mistaken for its baseline state. According to the research team, the method behind this discovery wasn't some brand new instrument or a fresh spacecraft. Dr. Robert Allen, the study's lead author, explained that the team took a comparative approach, examining the original Voyager 2 data side by side with decades of subsequent observations, made much closer to home, at Earth. This is not chaos. This is strategy. Scientists essentially built a translator using nearly 40 years of accumulated understanding about how Earth's own radiation belts behave during solar storms, and then applied that hard-won knowledge backward in time, onto a single afternoon of data collected by a spacecraft that has long since left the ice giant far behind. The study indicates that Uranus may have been experiencing a significant space weather event during that exact flyby, an event that appears to have generated the strongest high-frequency waves detected during Voyager 2's entire mission. Here is where the story gets its sharpest twist. At the time of the original flyby, scientists believed those high-frequency waves would scatter energetic electrons, causing them to fall harmlessly into Uranus's atmosphere and disappear. But research conducted since then has shown that under certain conditions, those same waves can do the exact opposite. Instead of clearing electrons away, they can accelerate them, injecting even more energy into a planet's radiation belts. In other words, the mechanism scientists assumed was calming the storm may have actually been feeding it. For 39 years, the interpretation ran backward, and nobody could have caught the error without decades of independent observations that simply didn't exist yet in 1986. This is the real story, not that Voyager 2 made a mistake, but that humanity needed 40 more years just to catch up to what it had already told us. Think about what this means for the future of planetary exploration. Uranus has never had an orbiter. It has never had a dedicated return mission. Everything we think we know about its interior, its magnetic field, its moons, and its rings comes from that single 5.5-hour window in 1986, filtered through the scientific understanding of an era that didn't yet have the tools to interpret it correctly. Dr. Allen himself noted that science has come a long way since that original flyby, which is precisely why a comparative approach against modern Earth observations was even possible. And this new finding does something quietly dramatic to the argument for actually going back. The discovery reshapes how scientists think about Uranus, and researchers now argue it deserves another visit. If the only data set we have was skewed by a freak solar storm the entire time, then an ice giant that scientists spent decades believing they understood might, in reality, still be almost a complete mystery. But this is only half the story, because while researchers on Earth were quietly rewriting the history of a flyby that happened before most of today's mission scientists were even born, the spacecraft that made it all possible has been fighting its own battle, one that has nothing to do with planets and everything to do with survival. Voyager 2 is dying. Not suddenly, not dramatically, but on a slow, carefully managed countdown that engineers at NASA have been monitoring for years. The spacecraft is equipped with 3 radioisotope thermoelectric generators, each containing pressed plutonium oxide spheres. And at launch, these generators collectively supplied the spacecraft with 470 watts of electrical power. But radioactive decay doesn't negotiate, and it doesn't pause for scientific breakthroughs. That power output has been halving roughly every 87.7 years. And while engineers originally predicted operations could continue only until around 2020, careful power management has kept 5 scientific instruments running well beyond that original estimate. Every additional year of data has been squeezed out through a kind of engineering triage, a series of increasingly difficult decisions about what stays on and what gets sacrificed. In April 2023, engineers at the Jet Propulsion Laboratory began drawing on a small reservoir of backup power that had originally been set aside for an onboard safety mechanism, a reserve nobody expected to need this deep into the mission. That decision bought time, but it also signaled something unmistakable. The spacecraft was running out of options. Then, in October 2024, NASA made the call to power down the plasma science instrument entirely, a deliberate sacrifice made specifically to preserve energy for the remaining 4 instruments still gathering data from interstellar space. Imagine being the engineer who has to choose which 47-year-old scientific instrument gets switched off forever, knowing there is no way to ever turn it back on, and knowing that the spacecraft carrying it is farther from human hands than anything else our species has ever built. And here's the part that should stop you cold. According to the most recent tracking data available this year, both Voyagers remain operational and are still communicating from interstellar space as of January 2026, though NASA describes them as being in a kind of survival mode nearly 49 years into their journey. According to NASA's own projections, these spacecraft will eventually fall silent once their power generators finally die, an event some estimates suggested could happen this very year, though the agency continues to hope the timeline stretches even further. This is not a hypothetical ending. This is a mission operating on borrowed time right now, while it is simultaneously producing one of its most significant scientific reinterpretations in decades. The discovery about Uranus's radiation belts isn't happening during some golden, well-funded era of the mission. It is happening during its final act, pulled out of archived data, because the spacecraft itself can no longer generate the kind of fresh readings that once defined its glory years. And there is something almost impossible to comprehend about the sheer distance involved in all of this. As of February 2026, Voyager 2 sits roughly 143 astronomical units from Earth, a distance of over 21.4 billion kilometers, or more than 13.3 billion miles. A radio signal traveling at the speed of light takes close to 20 hours just to reach it one way. That means every command NASA sends takes almost a full day to arrive, and any response takes another full day to come back. A conversation with Voyager 2 unfolds across roughly a day and a half per exchange. A spacecraft so far from home that even light itself, the fastest thing in the universe, moves through it like a message in a bottle crossing an ocean nobody can see the other side of. Voyager 2 crossed into the interstellar medium on November 5th, 2018, at a distance of nearly 119.7 astronomical units from the Sun, traveling at a velocity of over 15 kilometers per second relative to our star. That crossing made it only the second human-made object in history to leave the protective bubble of the Sun's influence, following its twin, Voyager 1, by 6 years. But here's the detail that tends to get buried under the historic significance of that milestone. Voyager 2 didn't cross that boundary with the exact same set of working instruments as its sibling. It carried a different combination of functioning science hardware, which meant that when it finally punched through the heliopause, it recorded measurements Voyager 1 simply couldn't capture. 2 spacecraft, launched within weeks of each other, ended up giving humanity 2 different perspectives on the exact same threshold, separated by years and by hundreds of millions of kilometers of independent trajectory, and both perspectives turned out to matter. What most people are not seeing, even now, is that this entire mission has always operated on a kind of delayed revelation. The Great Red Spot's drift wasn't obvious until Voyager 2 compared its own images against Voyager 1's. The strange, felt marker-like linear features on Europa's icy surface weren't understood as signs of a hidden ocean, until scientists spent years studying what those cracks implied about tidal heating. Voyager 2's closer, higher resolution images revealed that those features lacked any real topographic relief, prompting one scientist to remark that they looked as though they had been painted onto the surface with a felt marker, a strange and almost dismissive description for what later became one of the strongest early hints that Europa might be hiding a liquid ocean beneath its ice. Even Neptune, the mission's final planetary target, kept secrets that took years to unpack. The spacecraft discovered wind speeds in Uranus's atmosphere reaching as high as 450 miles per hour, and evidence pointed to a boiling ocean of water, buried some 497 miles beneath the planet's visible cloud tops, a detail that reshaped how scientists imagined the internal structure of ice giants generally, not just Uranus specifically. This pattern, discovery followed by decades of quiet reinterpretation, is not an accident. It's the defining rhythm of the entire Voyager legacy. And it raises an uncomfortable question that most coverage of this mission conveniently avoids. If it took 39 years for scientists to correctly interpret the Uranus radiation belt data, what else is still sitting inside the Voyager 2 archive? Misread, misunderstood, or simply never revisited with the right modern tools? Well, this isn't a rhetorical flourish. In March 2020, NASA astronomers reported detecting a large atmospheric magnetic bubble known as a plasmoid being released from Uranus into space, a phenomenon they only identified after going back and reevaluating old flyby data years after the fact. That's two separate major reinterpretations of the same single 5.5-hour encounter, arriving years apart, each one changing how scientists understood the planet, and there is nothing that guarantees this is the last one. So where does that leave us? A spacecraft launched during the Ford administration, carrying computing power that today sits inside a musical greeting card, is currently running on emergency backup power roughly 21 billion kilometers from the people who built it. And it just forced a rewrite of planetary science using data that has been sitting in storage since before most of its current mission engineers were born. It is doing this while missing one of its 5 original instruments, permanently and irreversibly switched off to conserve the little power it has left. And its remaining lifespan is now measured not in decades, but potentially in the handful of years or even months that NASA's most recent power projections allow for. Humanity is still actively recalibrating exactly how much time it has left with a machine that is simultaneously delivering some of its most important scientific findings in years. Meanwhile, Voyager 2's twin Voyager 1 is on track to become the first human-made object ever to reach a full light day from Earth, expected later this year, a distance so vast that precision in tracking suddenly matters more than ever. And that leaves us with the real unresolved question hanging over everything. Researchers openly acknowledge that some of today's unexplained observations from the Voyager archives may become tomorrow's major discoveries, and others wonder whether future analysis could uncover patterns nobody has recognized yet. There's no confirmed evidence of anything beyond natural planetary phenomena inside this data, no hidden signal, no impossible reading that points towards something beyond known physics. But history has shown, again and again, with Europa's cracks, with Uranus's radiation belts, with a magnetic plasmoid nobody noticed for over 3 decades, that the significance of what Voyager 2 recorded is not always visible the moment it arrives. Sometimes it takes 40 years, an entirely new generation of scientists, and a completely different spacecraft's worth of comparative data just to ask the right question of information that has been sitting quietly in an archive the whole time. So the real question isn't whether Voyager 2 has made its biggest discovery yet. It's whether we would even recognize it if it already has. Somewhere in nearly 50 years of transmitted data, in readings taken during those 5.5 rushed hours at Uranus, or during the long, silent decades crossing into interstellar space. There may be another anomaly sitting exactly where the radiation belt mystery sat for 39 years, unexplained, unremarkable, waiting for the right mind and the right decades of comparative Earth data to finally make sense of it. And the spacecraft that recorded it is running out of power, right now, faster than anyone would like to admit. The question is no longer only what Voyager 2 will discover next. It's how much of what it already told us decades ago we still haven't learned how to hear.